Hey guys, welcome to All Electronics. In this video, we are exploring three different methods for characterizing the dielectric constant of a PCB substrate. Knowing the effective permissivity of a PCB is essential for microwave designs, as all the geometries of microstrip, filters, resonators are based on permissivity. The first method we are going to explore is the ring resonator. We can measure the frequencies where it resonates and use that to back calculate the properties of the material. We also gonna be exploring a method using phase measurement. By measuring the phase response of different microstrips, we can estimate the electrical length of each microstrip and back calculate the effective permissivity. And at the end of the video, we're gonna go to the time domain, measuring the reflections generated by impedance discontinuities in a transmission line like this one here. This video is based on an article I wrote. The link is in the description of the video. This is real engineering, because you're watching All Electronics. First method we are going to explore is the ring resonator. Just to clarify, what we are trying to do here, guys, we are trying to measure the substrate dielectric constant, or permissivity. I bought this PCB material for the projects of the channel and I don't know its dielectric constant. So we need to measure it to be used when we are developing and designing filters, resonators and things like this. This is 0.8 millimeters FR4 double-sided as we use here on the channel. The ring resonator consists of a ring, a microstrip ring, and two feeding lines or coupling lines. And you can see that the lines are not touching the ring. The energy is coupled to the ring with a very small gap, and we expect this structure to resonate at a certain frequency. So we can use the VNA to measure the resonance and back calculate the dielectric constant of the PCB. Here you see the ring resonator, the two feed lines and small gaps coupling the energy. I calculated a radius for the ring that creates a 100 millimeter circumference. The total length, the physical length of the ring is 100 millimeters. And here is the key observation about this method here, and actually about the other methods also. 100 millimeters is the physical length of the resonator. If we calculate a resonance frequency, a wavelength of 100 millimeters, we are going to get a resonance frequency. But when we perform the measurements, we are going to see the resonance frequencies are much lower than that. And this is because the electrical length is greater, and the dielectric constant, the factor that we are going to measure, the constant that we need to measure, is what defines the relation of propagation speed for the electromagnetic wave. So what happens is that the electrical length looks bigger than the physical length because the speed of propagation is reduced by the substrate. And in practice, is this reduction in speed, propagation speed, that we need to characterize so we can use this constant in future designs. Here we see an S21 plot, the transmission between one port to the other as we expected. We see the first resonance here, and actually we see resonances at integer multiples of the first resonance. This is because this ring can resonate in multiple harmonics of its fundamental frequency. There in the article you can see a better explanation about this and also an animation showing the resonance behavior of the ring. We see the first resonance at 1.56 gigahertz. We expect the next resonance to be at double that value. And indeed, we have it. And here, 3 times the fundamental resonance. Yes, you can see that the coupling is very low. We are operating at negative 35 dB here in the maximum peak. So the transmission is very low, and this is very important. It's important that we keep the transmission very low because we can't load the resonator. Remember that the input and output are connected to fifth ohm lines, to the VNA, fifth ohm ports. If we connect the ring to a fifth ohm load, we'll be loading the resonator, shifting its resonance frequency. This is key because I see a lot of experiments about resonance where the resonator is actually loaded, and in that case you would not be measuring the correct resonance frequency of the unloaded resonator. So the idea here is that we need to adjust the gaps to keep the coupling very, very low and not too low that we cannot measure it. I realized that the coupling needs to be controlled so the transmission is not greater than negative 25 dB. What is fascinating about using a ring resonator is that we can actually measure the dielectric constant at different frequencies. We have an automatic sweep of the measurement, right? We can back calculate it here, back calculate it here, back calculate it in all the resonant frequencies of the ring. And we can even calculate the Q factor of a resonance by measuring its bandwidth. And the reciprocal of the Q factor is the loss tangent. If you back calculate the loss tangent here, you're gonna see that we get 0.02. That's more or less what is expected for FR4 material. Now we need to get the resonant frequencies and back calculate the dielectric constant of the PCB. What I did was to export the CSV trace from the VNA, and I created a Python script that automatically finds the peaks and make the calculation. You can see that on the article. All the scripts that I use it are available on the Patreon post, and remember that you can support my work, support the channel for more videos like this by becoming a patron of the channel. Link is in the description. This is the equation, guys, for the resonant frequency of the ring resonator, or actually any resonator that's resonating at one wavelength, based on the harmonic number, like the fundamental, this peak here, or the next harmonics. This is n equals 1, n equals 2, right? And here we have the effective permissivity, or the effective dielectric constant. This is very important, and I will explain the difference between the effective dielectric or the dielectric of the material. But let's first try to understand this equation. You can see that this equation is actually very simple. It's just the speed of light divided by the wavelength, right? By the length, the physical length of the resonator, 100 millimeters for this case here. And of course we multiply by n, because for each higher harmonic we are fitting inside the ring more than one complete wave cycle. So for one here we have one wave cycle inside the ring. For the second harmonic we are fitting 2, because it works as if the speed of light was quicker, because we are fitting more than one wave cycle inside the ring. And you see that the square root of the effective permissivity and dielectric constant is the same, so I will be changing this around. You see that the square root of the effective permissivity is dividing the speed of light, exactly because this is the speed factor, is the velocity factor of this structure in this material. And a different point of view is that it is increasing the physical length. So this combination here creates the electrical, right? Is the electrical length, is the length that the wavefront will experience. You see that this is multiplying L and creates a larger length. The electrical length is larger than the physical length. This is just a different point of view. You can think that the speed of light is being reduced, or the physical length is being enlarged by the speed factor. It doesn't matter. This constant is what we need to discover. So we can just rearrange the equation. You can do it yourself to find the effective permissivity by the frequencies that we measured on the VNA. And now comes an important part, guys. What's the difference between the effective permissivity, or the effective dielectric constant of the material, to the material relative permissivity? What happens is that the electromagnetic field for a microstrip like this one here is not fully embedded on the material. Part of the field lines go from the microstrip to the backplane, to the bottom ground. These field lines are experiencing the material dielectric constant, but part of the field lines are propagating in the air. They are twisting around here and they are experiencing the relative permissivity of air. So what ends happening is that we have, for a microstrip geometry like this, an effective permissivity that is a permissivity in between. That makes sense, right? We could conclude this by intuition. We have a permissivity that is in between the air permissivity and the material. Actually, what happens is that for any method that we are going to use to make a real measurement, we are always measuring the effective permissivity. We are always measuring the effective permissivity, because we are measuring the real thing. We are always measuring the combination for this microstrip geometry of the material's permissivity and the air permissivity that becomes the effective. So after we back calculate, we have the effective permissivity. This measurement will be approximately 3.6. And for you to see the difference, commonly FR4 has a relative permissivity 0.5. So you see that the measurement is lower for 0.5 and is higher than 1. That would be the relative permissivity for air. So what I did on the article, you can see that I used equation. We can use equations that are actually empirical equations that calculate the effective permissivity from the relative permissivity of the material for a given microstrip geometry, where we need to input the height of the substrate and the width of the microstrip line. And what can we do here? We can use these equations here in reverse also. We back calculate the effective permissivity from the frequencies we measure, and as we know the height and we know the width, we back calculate again the relative permissivity. And that's why it's easier to automate all this calculation using some scripts instead of doing it by hand. For this specific FR4 that we have here on the lab was around 4.8. So now let's explore a different approach to measuring the effective permissivity. And actually I'm looking forward to show you the time domain method. For me this is the most fascinating, so stay with me, we are going to see this on the end. The idea here, guys, is to measure the phase response and again back calculate the effective permissivity. But why use a pair of microstrips? We can consider just the increment in length between both lines, canceling in some way the effects of the SMA connector. Because imagine that we just measure one microstrip, measure its electrical length. This hypothetical measurement would include the electrical length of the SMA connector also, and also the electrical length between the transition from the coax median to the microstrip median. By having two lines, in theory, we can consider just the increment and cancel the effects of the SMAs. So let's connect it here. Of course, for the real measurements I used an SMA wrench, and we are going to measure actually for S11. And of course, guys, is 0, right? Up to this resonance that is actually the microstrip radiating. That line makes a very good antenna at 10 gigahertz. Interesting. All the energy is reflected back because we have an open termination here and we see a 0 dB trace for S11. You can read that as 100% reflection. So the proper way of measuring the length, the electrical length, is by looking at the phase. Look at this. So we see exactly the behavior of the wavefront as it propagates and reflects on that line. And as the frequency increases, we see the periodic behavior. We can fit more and more wavelength on that physical length of the line. As I said, if we try to back calculate the electrical length from that phase profile, we would be including the SMA and the transition between coax to microstrip in the calculation. We also would be including any miscalibration between the analyzer port and the microstrip. Let's see now what happens when we superimpose the measurement of the other trace. So we can actually save this trace to memory and display data and memory. Now we are going to swap the trace to the larger one. And of course, now that we are measuring the larger trace, the periodic behavior happens first. Look at this, the transition here, because we can fit a lower frequency inside the electrical length of the microstrip. And as the frequency increases, this difference also increases. Phase profile is directly related to the electrical length of the microstrip. And having the two measurements, we can create a system of equations that compute the electrical length, thus the effective permissivity, using the two phase profiles and the length difference, not relying on the absolute length of the microstrips, so canceling or removing the effects of the SMAs. Now we're going to characterize the material using a time domain method. And why my emphasis on the time domain method? Because the methods that we experienced up to now are frequency domain methods. The VNA is sweeping the frequency and making the measurements. Time domain is very interesting because the universe, the world, works in the time domain. So what we are going to do is that we are going to generate a very fast pulse that will propagate in this microstrip geometry here. And this microstrip geometry is very special because it has a 5th ohm transmission line, the narrower trace, and also two impedance discontinuities. One discontinuity here and another one here. As the pulse propagates, and the propagation happens in time. This is why time domain methods are so interesting. As the pulse propagates, it will collide, it will reach one of the impedance discontinuities, and part of the energy will be reflected back. So if we put an oscilloscope here on the port also and monitors the voltage here, we are going to see over time small positive or negative pulses of voltage that are actually the energy reflected back arriving at the port. So the main idea is that if we capture the time between two discontinuities, between two pulses on the oscilloscope, as we know the physical length, we can back calculate the electrical length or back calculate the effective permissivity. When traveling back, both the reflection signals will pass to the connector. So the effect of the connector is equal to both pulses, and in some way we are cancelling the effect of the connection. To generate the very fast pulse, we are going to use a BJT transistor working in avalanche mode. This is something that I want to explore in next videos, and I have been trying a lot to generate very fast pulses using very few parts. So here we have one of my prototypes. Here in the middle we have a very small transistor that is avalanching, and it generates a very fast pulse. The circuit is supplied with 32 volts and a trigger pulse coming from a signal generator. By connecting it directly to the oscilloscope, we can see the shape of the pulse. We can see that the generated pulse is very clean, and it has approximately 200 picoseconds from the midpoint of the rise edge to the midpoint of the falling edge. And indeed, it needs to be very short because this defines the time resolution that we have to distinguish different features over the geometry. So imagine that if the pulse is larger than the time difference of the transitions, we would not be able to see the different features in the time trace. This is very similar to the resolution bandwidth when we are dealing with a frequency domain measurement. Very fascinating. The pulse generator connected to the microstrip test board and with the oscilloscope monitoring the voltage in this port, we will be able to see the reflections happening and time the difference between them. Let's take a look. Look at this, guys, this is so nice. The biggest peak here is the pulse generated by the pulse generator itself. And after that, we see all the reflections happening. So this trace, this time domain trace, is actually the dual of the S11 trace in the frequency domain. This is the time domain reflection. Sometimes it's called T11. The first reflection wavefront is negative. This means that the wave encountered a high to low impedance, and after that it encountered a low to high impedance, and this is exactly the geometry that we have. So the pulse propagates and it encounters first a high to low impedance discontinuity, this negative wavefront here, and after that it encounters a low to high impedance discontinuity, this pulse here. And we are interested in measuring the difference between this discontinuity and this one here, because this length in between is, or reference length, is the well-known physical length. So we need to measure a low to high transition and a high to low transition. And this is exactly the 2 points that are marked here, right? We have this moment here and this moment here. And the difference in time between these 2 peaks is double the time the wavefront took to propagate from this point to this point. And why it's double? Because we are measuring reflections. So remember that the wavefront will first reach this point, after reach this point, and now the reflection is coming back. So always that we are measuring reflections, we need to divide the measurements by 2, because we are always measuring the time it took the wavefront to go forward and to come back. And we see that the difference is 884 picoseconds. We fire the pulse on the port and it starts propagating to the forward direction. When it encounters the first discontinuity, a negative wavefront is reflected back. This is the first reflection that happened. The original pulse keeps propagating, now with a little less energy, because part of the energy was reflected in the first reflection, but the rest of the energy keeps propagating forward and it encounters the second discontinuity. Now from a low impedance to a high impedance, creating a positive wavefront that travels back. This is reflection B. The same occurs for reflection C, and of course it also occurs for this reflection and the end of the PCB. So the signal that we measure that looked like something has reflection A here, reflection B, and reflection C, and we are interested in the delta time between these two reflections. And that delta time is 884 picoseconds. So now I have a challenge for you. Oh, sorry, here is 2 delta time, right? And the delta S, the difference in length here, this distance is 69.5 millimeters. And you know that to travel 2 times this distance, the pulse took 884 picoseconds. Now my challenge to you is try to calculate the effective permissivity. Try yourself. First of all, think about how long it would take if the velocity factor was 1. Just the speed of light. How much time it would take? Of course, by calculating using the speed of light, it will give a shorter time because the propagation velocity is reduced by the effective permissivity. And of course, if you're not able to calculate yourself, take a look on the article. There I have an explanation in detail about every aspect of this calculation. Well guys, I hope you enjoyed this video. If so, subscribe to the channel, give it a thumbs up, send to your friends, and I see you in the next video of All Electronics.